In the early hours of February 24, 1979, seismographs at the University of Utah recorded an earthquake strong enough that people nearby should have felt their houses shake. Nobody did. Not one person reported feeling a thing. For decades, that single contradiction sat quietly in the data, unresolved, mostly forgotten. Then, just months ago, a team of scientists finally confirmed what one young researcher had suspected all along. This earthquake happened 90 kilometers underground in a layer of the Earth where modern geology insists earthquakes simply cannot occur. Not rarely, not occasionally, according to the textbook rules of plate tectonics, this kind of earthquake should be physically impossible. So how do you explain something that broke the fundamental rules of seismology, and why is it only being confirmed now, almost 50 years later? Most people assume earthquakes are a crust phenomenon, full stop, something that happens in the relatively thin, brittle outer shell of rock we all live on top of. That assumption isn't wrong exactly, it's just incomplete, and the gap in that assumption is exactly where this entire mystery lives. To understand why this earthquake broke the rules, we first need to understand what those rules actually are and why they exist in the first place. The Earth's crust beneath continents typically extends down to about 30 to 50 kilometers before giving way to the upper mantle, a region defined by a boundary geologists call the moho. Above that boundary, rock is cold and brittle enough to crack and slip suddenly, which is exactly what an earthquake is, rock breaking. Below that boundary, conditions change dramatically. Temperatures climb past 700 degrees Celsius, pressure becomes immense, and under those conditions, rock stops behaving like rock at all. This is where most assumptions about the Earth's interior start to fall apart. People imagine solid rock as permanently rigid, something that either holds its shape or violently breaks. But deep in the mantle, rock does something stranger. As one of the lead researchers on this discovery put it, on long timescales, mantle rock behaves like taffy, not breaking suddenly, but slowly flowing and deforming over millions of years, the same way thick candy stretches and bends instead of snapping. Rock that flows instead of fracturing shouldn't be capable of producing the sudden, violent slip that defines an earthquake. That's the entire reason mantle earthquakes beneath continents were considered essentially impossible for most of the history of modern seismology. So when a postdoctoral researcher named George Zant looked closely at the data from that 1979 Utah earthquake, what he found should have been a contradiction in terms. Zant was analyzing seismic readings from a magnitude 3.8 earthquake beneath a small town called Randolph, near Utah's border with Wyoming and Idaho. A quake that size should have rattled dishes and woken people from sleep. Nobody reported feeling anything at all. When Zant traced the timing of the different seismic waves arriving at various recording stations, the math kept pointing to the same impossible answer, a focal depth of roughly 90 kilometers, deep inside the upper mantle, far below where conventional earthquakes are supposed to be able to happen. He published a short technical note about it, and then, for decades, almost nobody paid attention. This is the part of the story that should genuinely frustrate anyone who cares about how science actually works. A correct, groundbreaking observation sat quietly ignored for nearly 50 years, not because it was wrong, but because it contradicted an assumption so deeply embedded in the field that almost no one thought to seriously question it. The turning point came when a new generation of University of Utah seismologists, led by geophysicist Keith Koper, decided to revisit Zant's old data alongside 8 other suspicious, unexplained deep earthquakes recorded in the same region over the following decades. Using updated analytical techniques unavailable in 1979, the team carefully recalculated the depth of all 9 events. Every single one confirmed the same impossible pattern. All 9 earthquakes originated well below the crust, deep in the upper mantle, at depths ranging from roughly 68 to 90 kilometers. This wasn't a single fluke anomaly anymore. It was clear evidence of an entirely overlooked category of earthquake. Researchers gave it a formal name: continental mantle earthquakes, or CMEs. But naming the phenomenon doesn't explain it. So what's actually happening down there that lets rock break in a place where it's supposed to flow instead? The answer appears to be tied to a specific ancient geological feature buried beneath this exact region, the Wyoming Craton, an extremely old, thick, and unusually cold slab of continental crust that has remained stable for billions of years. At the edges of this craton, where it meets younger, warmer, more typical crust nearby, conditions become genuinely strange. Researchers believe the boundary creates localized zones where colder, stiffer material gets dragged and stressed by the slow flow of surrounding mantle rock, occasionally building up just enough rigidity in just the right narrow conditions for a sudden brittle failure to happen anyway, even at depths where it theoretically shouldn't be possible. These earthquakes also behave differently from ordinary quakes in a telling way. They occur in complete isolation with no aftershocks at all, unlike typical crustal quakes, which usually trigger a noticeable sequence of smaller follow-up tremors. That absence of aftershocks itself supports the idea that something genuinely unusual is happening in the rock down there, a single, isolated failure rather than the gradual stress redistribution typical of shallow earthquakes. And this isn't just a Utah curiosity. While this research was unfolding, a separate team at Stanford was independently building the first global map of these elusive mantle earthquakes using a breakthrough technique capable of distinguishing the subtle seismic wave signatures unique to deep mantle events. Their map revealed something striking. These continental mantle earthquakes aren't randomly scattered. They cluster in specific regions around the world, notably beneath the Himalayas and near the Bering Strait, suggesting this phenomenon is tied to specific, identifiable types of geological boundaries, not random chance. Then, on September 10, 2025, while this research was still being finalized, Nature provided an almost perfectly timed confirmation. A new magnitude 4.1 earthquake struck near Mazer, Utah, with a calculated focal depth of 68 kilometers, more than 20 kilometers below the Moho boundary itself. The phenomenon Zant had first glimpsed in 1979 wasn't a one-time anomaly from old, possibly flawed instrumentation. It was still actively happening in real time, validated by modern equipment nobody could argue with. So why does any of this actually matter beyond satisfying scientific curiosity? Understanding where and how these deep mantle earthquakes occur gives researchers an entirely new window into the boundary between Earth's crust and mantle, a region that's notoriously difficult to study directly. It also raises a more unsettling question for seismic hazard planning. If earthquakes can occur at depths and in rock conditions previously assumed to make them impossible, our basic models for predicting where dangerous seismic activity can happen may need meaningful revision, particularly in regions sitting near ancient, unusual geological boundaries like the edge of a craton. A discovery first glimpsed by one careful postdoctoral researcher in 1979 sat almost entirely ignored for nearly 50 years until new technology and a fresh set of eyes finally proved he had been right the entire time. The Earth, it turns out, still has rules we haven't fully figured out, sometimes hiding in data we already collected decades ago, waiting for someone to simply look again. If stories like this make you think differently about how much we still don't understand about the ground beneath us, stick around. There's a lot more hidden in this planet's depths we haven't covered yet. And let me know in the comments, if a single researcher's correct discovery can sit ignored for 50 years, what other settled science do you think might eventually get turned on its head?